One very common question you might be getting, and I want you to try this out for yourself, is what would this look like what would acceleration due to gravity, all right, look like as a position versus a time graph, a velocity time graph, or an acceleration time graph? What would an object in free fall? So take a few seconds, try it out yourself, and come back. Hit pause. I'll be here when you get back. All right, so welcome back. Let's try this out. Now, there's probably a couple ways to do this. I'm going to show you the way my brain works with it. So there's a position versus the time. Here is a velocity versus the time. And here is an acceleration versus the time. Now you could do this many ways. I'm going to show you the way my brain works at this. My brain picks the fact that acceleration is constant. So free fall is constant. Okay, and it's constantly going to be negative 10 meters per second squared. That is what our gravity is. So with that knowledge, I can draw it just like this, because it doesn't change. And I'll label it over here, because that's what gravity is. All right, now from there, I can kind of start thinking my way back. So if it's dropped, okay, so velocity versus time graph is dropped. That means if something's dropped, my brain tells me that the initial velocity is going to be 0. Okay, so it's 0 and it's coming back to Earth. All right, and I say the Earth is the origin. That makes the velocity becomes negative. Okay, so velocity starts at 0 and it's going to be negative. That means it's all going to be on this side right here. Okay, and what happens when things drop? They get faster and faster. So in that case, I start at 0. I need to get faster and faster. Okay, so in this particular case, if I would take the slope of this line, that slope would be gravity. So let's take this same idea, okay? And for a position versus time graph, right here, if the initial velocity is 0, I'd be saying this is my 0. All right, whoops, except back myself up here. That's going to be wrong because I'm not starting at position 0. I'm starting away from the Earth. Okay, so my initial velocity is 0, but I am away from the origin. I'm going to speed up back, coming back. So I start at velocity is 0, and by the time I get back to the origin, back to Earth, I'm going fast. So I see right here, I've got 2 different lines. That's a flat slope. That's a steep slope. So now, I'm just going to put these 2 lines together. A little bit smoother would be nice, but that would be how I would draw those 3 graphs. And that's my thought process. One of these would be a really great test question, just heads up. Okay, so now we're going to go through the 3 special cases of free fall. We've seen what it looks like graphically. Now let's do these 3 special cases. Special case 1 is dropped objects. In this particular case, our initial velocity in the y direction is 0. Our acceleration in the y direction is negative 9.81 meters per second squared. We could also go ahead and say that that would be about negative 10 meters per second squared. I was going to draw this, all right, and now's the time we're going to start drawing things out as well. It would look a bit like this. Here's a cliff. Here's my object. And I'd be writing it out like this. Okay, if I knew this, I'd put that over there. That'd be kind of how I draw that out. Now this next question is final position at top. It is sometimes asked as how high. Okay, in this particular case, the final velocity in the y direction is 0 meters per second. Acceleration due to gravity in the y direction is negative 9.81. which we know is going to be about approximately, that's what a little squiggle line is, negative 10 meters per second squared. If you're going to draw this one, it should look something like this. Okay, that's kind of how we do this. We might draw like VIY here, VFY equals 0. If you know it, you'd put your delta y in there as well. Our third scenario is when you throw something up into the air and so this would be our 0, right? Throw it up into the air. Whoa, excuse me. Throw it up into the air and you catch it at the same height. That means your delta y is going to be 0. It also means, because of symmetry, that your initial velocity in the y direction has to equal the negative final velocity in the y direction must equal the negative of the initial velocity. And that's basically because as you're going up, gravity is acting on it every 10 seconds, all right? Every second, the speed is changing by negative 10 meters per second. But that same change is happening on the way down, okay? So because gravity acts on it the same, okay? It's because gravity acts on it the same, that's how we get that symmetry. It also means that our time up must equal our time down. So we would say that time up equals time down. We'd also say that, let me see here, that our total time will be equal to the time up plus the time down. Just features of the symmetry. Thanks. Okay. So there you go. Those are our 3 special cases. Dropped objects, how high, and returns to the same position. Now I'm going to go ahead and give you 3 examples. We'll pause here. We're going to do this first, this section right here. Take a few seconds, sketch this out on your page, and I want you to come back and I'll go ahead and we'll go over the answers for this. All right, welcome back. First thing to note is that gravity acts all the time, okay? So that means the acceleration at each point is going to be negative 10 meters per second squared. Okay. Even at the top. Now it's very easy to think that it's not there at the top. All right, because you're likely already aware of this, that the velocity at the top is 0. All right, that 0 velocity does not mean 0 acceleration. It's still being acted upon by gravity. That gravity is actually what's causing it to change direction. Remember, acceleration is the speed can go up, the speed can go down, or it can turn. And that's what we're seeing here, is we're seeing that turn of speed, okay? All right, and so this is not a chunk of time. This is a bare instant, okay? So let's keep going here. So because of symmetry, if at VA it's 12 meters per second, that means if you catch it at that same height on the other side, it'll be negative 12 meters per second. And if at VD is negative 4 meters per second going down, at VB it must be positive 4 meters per second going up. Okay, so that would be how that would look. All right, take another second, and I want you to go ahead, hit pause, and I want you to answer when I'm done talking, and I want you to fill in the values for the variables on the first question right here. An object is thrown 3 meters per second from the ground, and it lands on the ground. I'm going to put in these values right here. So you're basically pulling in your givens. Now, one thing that's really important here, and a lot of us have problems with this, okay, when we're throwing things up and throwing things down, we don't care about what causes the motion or what stops the motion. We only care about it in the air. So in a scenario like this, it's from the instant it leaves, the instant it starts moving to until just before it stops moving. Okay? However they phrase it, when you're talking about stories like this, it's just that bare instant after it starts to that bare instant before it stops. So hit pause, try this out, come back in a few seconds. All right, so for the first problem, if an object is thrown 3 meters per second from the ground and it lands on the ground, well, our initial velocity, because the story starts there, is 3 meters per second. So if it's from the ground and it lands on the ground, that means our final velocity is negative 3 meters per second. Okay? Because the only thing acting on it is gravity. That's negative 10 meters per second squared. Because it starts and stops in the same place, our delta y is, our displacement is 0 meters. Go ahead, do the same thing, hit pause, and answer the variables for this question. An object is thrown into the air going 80 meters per second. How high does it go? Try and identify these variables: initial velocity, final velocity, and acceleration. Okay. So if an object is thrown into the air going 80 meters per second, its initial velocity is going to be positive 80 meters per second. Its final velocity is going to be 0 meters per second. And its acceleration is going to be negative 10 meters per second squared. Okay. So that'd be how you go about grabbing the variables. Let's go do a couple samples. Actions. All right, special case number 1. All right, you are welcome to go ahead and hit pause after I read the question and try them out yourself, and then come back. Okay, so we're going to start with this. An object is dropped from a 15-meter ledge. How fast is it moving just before it hits the ground? All right, so think about code words here. All right, and one big code word is, how do we know it's a free fall problem? The one easy way to know it, there's only one number in here. It's a good code, good reason it's a good code. It might be a free fall problem. So hit pause, try it out yourself, and then come on back. Okay, let's try this out together. We're going to start by putting out all of our variables. Okay, we've got delta x. Not delta x, we're doing delta y. We got our initial velocity in the y direction, our final velocity in the y direction, time, and our acceleration in the y. Let's go through here. So it's dropped from a 15-meter ledge. Okay. Okay, so we're saying 0. Okay, you gotta decide where you're gonna put your stuff here. So we see, okay, it's got 15 meters. Our initial velocity is 0 because it's dropped. Meters per second. Because it's dropped, we know that means there's gravity. So that'll be approximately negative 10 meters per second squared. We know how fast is it going just before it lands, because we have no t. So the only equation that doesn't have time in it is final velocity squared is equal to the initial velocity in the y direction squared plus double our acceleration in the y times displacement in the y. Okay. So if this is the case, to find our final velocity in the y, we just have to square root both sides. So final velocity will equal to the square root of the initial velocity squared, which is 1, plus, okay, brain stopping, all right, plus 2a y delta y, okay, that's going to equal to 2 times negative 10 meters per second squared times 15. If you're looking at that, that's not going to work because that would be taking square root of a negative number. So what happens here? So here's what it is. The height is 15 meters, but our displacement is 0. It's negative 15 because our displacement is y final minus y initial. If this is 0 and this is 15, 0 is our final, 15 meters is our initial, so therefore we get negative 15 meters. That's why that should be a negative. So now we've got, you see, the square root of 300 meters. And that is going to be plus or minus 17.3 meters per second. So now you got to choose it's going to be the plus or the minus. And I'm going to choose it's negative 17.3 meters per second is our final velocity in the y direction because it is going down. All right, keep moving. Next case, I'll read it. You can hit pause and come back. It says a ball is thrown 24 meters per second into the air. How high does it go? Hit pause, try it out yourself, come on back. All right, so again, one number is a clue, it's in free fall. That it's thrown is another free fall clue, code word. And it's thrown 24 meters per second into the air, so it's going up. That tells us it's positive. It's the beginning of the story, so it's our initial velocity. How high does it go? Tells us that the final velocity, this is what we're looking at. That's what it's looking for. This is our initial velocity. This is our final velocity. Little pictures can always help you out. Final velocity is 0 meters per second. Our acceleration, okay, so acceleration in the y direction is about negative 10 meters per second squared. And we're looking for delta y, which means we don't care about time. So it's the same equation we just used. Final velocity squared is equal to the initial velocity in the y direction squared plus 2a in the y direction times delta y. Now when this happens, this one goes to 0 because that final velocity is 0. So we're just going to move this over. Okay, we're subtracting it, not turning it negative. Okay, that becomes 0. So we've got minus the initial velocity in the y direction squared is equal to 2a y. There's delta y. We're solving for delta y, so we're going to divide both sides by 2 times the acceleration in the y direction. That will go away. So we're left with minus the initial velocity in the y direction squared divided by 2 times the acceleration in the y direction. And that will become minus 24 meters per second squared divided by 2 times negative 10 meters per second squared. Let's go plug that in. We're left with negative 576 meters squared per second squared divided by negative 20 meters per second squared. All right, the two negatives, negative and negative, turn into 1. Second squared. That's 1. And then one of our meters, we'll cancel out the meters on bottom. And 576 divided by 20. All right, that becomes 28.8 meters is our vertical displacement. All right, that's our second case. That's our how high. Third case, special case of a person throws a tennis ball 6 meters per second straight up. How long does it take for it to come back to their hand? Okay, so again, try this one out on your own. Come on back, we'll try it out together. All right, let's take a look at this one. I'm going to sketch it out over here on the side real quick. Okay, what I know here, based off everything, I know this initial y And that's our final y, and because of symmetry, that will have to equal that. Okay. All right. Okay. There's all sorts of ways. Let me see. So we know that it is thrown up into the air at 6 meters per second. We know, all right, our final velocity in the y direction would be negative 6 meters per second. Our acceleration is going to be, because it's a throwing, is going to be negative 10 meters per second. And we're looking for how long. Okay. So that would be question mark. All right. I'm not going to mess with the delta y because that delta y is 0. And on some of the equations, that's going to be kind of weird. So we're going to ignore the delta y. That's going to be the one we don't have. We're going to say we don't have. So we're going to work off of these guys. So we've got final velocity. So the one that does not have delta y in it, because that 0 can mess up some of our equations, is equal to initial velocity in the y direction plus acceleration in the y plus time. You have to pay attention to your variables here because you can get real messy real fast. All right, oh, something I told you not to do. We're going to solve for time. So the first thing we're going to do, we got to move the initial velocity in the y direction over. That becomes 0. So we're left with final velocity in the y direction minus initial velocity in the y direction is equal to our acceleration in the y times time. All right, before I move that acceleration in the y over, I'm going to remind myself that is now an entire term. Put parenthesis on it. Divide both sides by the acceleration in the y. And that will tell us that time is equal to final velocity in the y minus initial velocity in the y divided by acceleration in the y. So it's negative 6 meters per second minus 6 meters per second divided by negative 10 meters per second squared. We'll do all that math. Negative 12 meters per second divided by negative 10 meters per second squared. Okay, so our meters will become 1. Some of our seconds are going to disappear. We're left with just one of them. That's going to flip up to the top. So 12 divided by 10 is 1.2 seconds is the amount of time that it takes to come back. And there's all of our problems. All right. Thank you for your time. Let me know if you have any questions. See you tomorrow.